So, a very good morning to all. And in this today's last lecture of mine, I will try to push through and try to use the configuration of root system to assign some kind of diagrams to the corresponding root systems, and which we call as a Dinkin diagram. So for that, let us let us start with the recalling what we did in the last lecture. Recall lecture 2. The main story of lecture 2 is, so we have, so what we defined a very crucial element. We considered the set V regular. So first of all, let us that we have V phi as our vector space and root system. Then considered V regular is nothing but V minus union of all H alphas belongs to phi, where is complement of all union of hyperplanes. And using that, we define the connected components of V reg are nothing but chambers. Okay. Now using chambers, we defined the notion of positive and negative roots. Okay, we defined positive. We didn't stop there, and using further, we defined indecomposable, namely known as simple roots. Of course, these are all relative to the chosen chamber of the root system. Once you have fixed chamber, then the simple roots are kind of assigned with that. Yeah. Later we focused on, so what we have is R of C is equal to R plus C, disjoint union R minus C. And the thing is that every element of R plus C is contained in non-negative integral combinations of B of C, where B of C is the set of all indecomposable roots of R. Okay, R plus. Similarly, R minus has that decomposition. So it is very crucial improvement from what we have. And what is that? These simple roots plays a pivotal role in classifying these simple Lie algebra, the so-called simple Lie algebra. At least we would come to know what we are expecting to be a simple Lie algebras. Okay. So what is more application of those things that we considered while group and proved that W is nothing but WS, whereas WS is nothing but generated by all the simple reflections. This BS is nothing but, we have not proved that. I think we were close to proving that. I hope everybody, like every participant, give an honest try of proving that. Yeah. So what was that? So this W originally we defined as the subgroup generated by all S alpha. Alpha belongs to phi, but seems to be that definition is redundant. Like lot of redundant part is there. Like this is actually excessive part. Lot of part of that is redundant. So you can have this as generated by S alpha I, where alpha I belongs to B of C. Okay. So that is a very crucial improvement. Fine. So what it is? So we have these things. So what to do? Now, using these simple roots. So let us begin. What we had R first actually. Sorry, not R. It is phi. Always confused with Bourbaki. So this is phi. Then, so I hope I have written the same thing. Yeah. So here again, I jumbled in phi of C in these things. So this should be, I apologize for the notational confusion. Phi of C is phi plus of C, disjoint union phi minus of C. Is obtained in, right? Yeah. Okay. So we started with phi, then we fixed a chamber, then we made its union, and then we went to B of C. Okay. And what does B of C gives us? This gives us A, which is called as a Cartan matrix. What is Cartan matrix? This is a matrix with integer. This entry is ijth entry is as n of alpha I, alpha j, where ij runs from 1 to L. This is actually L cross L matrix. Okay. Yeah. So we want to, what do you say about these things? How does it look like, this matrix? Anybody from the audience? How does this matrix look like? What are the diagonal entries of the matrix? Yes?
2.
Yes. So the diagonal entries of the matrix is 2. So what about non-diagonal entries?
It's a symmetric matrix.
Yeah, I think you should be better careful. Is it symmetric?
No. Sorry.
Yeah, no problem. So it is not symmetric because n of alpha I, alpha j need not be n of. See, note that alpha I and alpha j may have different norm, right? Isn't it? Yeah. And so, what you know, whether it is a non-diagonal entries, are I'm interested in positive or negative. What are those?
They are negative.
They are negative. Why they are negative?
We know that for the base elements, the n alpha I, alpha j are negative.
Yes, because they form which angle? Their
Acute
inner
angle.
product is less than 0. No, they have an obtuse angle with each along, right? Isn't it? So these are all negatives actually. These are note that this is actually an integer matrix. Okay, integral matrix. Okay, it's a very special kind of matrix. Okay, with these things. Yeah. So, I mean, we wish it could have been these things. And so what happens is, with respect to this, you would have a positive definite W invariant form on Rn. Actually, will have this matrix is positive definite. Okay, and so we would like to classify all these positive definite integral matrices. See, you would like to assign some kind of graph or some kind of a tool to kind of, this is not an easy problem, but when here the graph theory comes in the picture, first of all, the first goal is first approach is to nullify the norm. Nullify norm means make them same norm, and so suppose you assume that they have uniform norm, to make the matrix symmetric. Okay, so what you do is you make your matrix symmetric. Okay, and assign a an combinatorial tool which is kind of a so called as a Coxeter graph, where that will help us to have a control on, I mean, will help us to find to nullify those which are not occurring. Okay, so what I mean is, I should be more precise. Here is the thing. First of all, I should make it clear that, so here is the exercise. So if phi is an irreducible root system, then you cannot have phi is equal to phi 1 union phi 2. I mean, phi is irreducible root system. And let B of C is its the set of simple roots of phi, then you cannot write B of C as a disjoint union of B1 union B2, where every element of B1 and B2 are orthogonal to each other for all alpha belongs to B1 and beta belongs to B2. I mean, yeah, that is the thing. It's very quick. Can one quickly tell me the proof of these things? Suppose this is an exercise I have given, so it doesn't make sense to ask you proof, but it would make me some kind of satisfaction if some of you try to attempt what should be the why should it this case cannot happen for the simple roots? Anybody? Note that B of C spans V, okay, your ambient vector space. So this V, suppose your phi is irreducible, then what we proved yesterday, that V is a representation as W. What is that representation? Are all of you reading what I have taken yesterday, or yesterday's notes I need to send again, but this is what yesterday we have proved very beginning of the class. How should be the representation V considered as a W representation when your phi is irreducible? Anybody?
Then B
Pradeep?
is irreducible. You want
Sorry?
B is a irreducible W representation.
Correct. So in case actually, so try to prove that let V1 is the R span of B1 and V2 is the R span of B2. Then you will have V1 as V1 direct sum V2 where I is equal to 1, 2 are non-zero W representations. Okay, and that will contradict the result actually. So try to see that this is a trivial. I have given you almost the solution. Okay, so this happens. Okay, right. Yeah, now we want to make Cartan matrix in such a matrix such that is the thing. So what we'll do, so this is just to make sure that, so suppose I assign a graph with respect to that thing matrix, you will come to know what is that. So so let alpha 1, alpha 2, alpha L be the simple roots. And so we normalize them. So let EI is equal to, yeah, so all these are unit vectors. Okay. So unit vectors, and so by the thing, what is their inner product? This is just nothing but where theta ij is the angle is the angle these are all one, so you will have cos theta ij. Okay, and we know what is their angle. Their angle is obtuse angle, right? For example, theta ij in case of for A2, in the case of theta ij between alpha 1 and alpha 3, if you don't remember, is what is that angle? It is just nothing but 2 pi by 3. But how do you write cos 2 pi by 3? It is just nothing but cos pi minus pi by 3. So this is just nothing but minus cos pi by 3. Okay. So every angle will be a obtuse angle, and so you will able to write cos theta ij is equal to, in case of these root system, pi upon mij's, where in the root system case mij's are I am not writing arbitrary things. I am writing, please check the table. And so that's what we have proved yesterday. These tables with these obtuse angles, these are the MIJs. These are the only possibilities we have. Okay. Now I will pause for some questions. In case if you have question, please ask it. Right away you can ask. Yes.
Whether that Cartan matrix is positive definite means it's not symmetric one. That Cartan matrix is. It's not a symmetric one. Whether we can say it is a positive definite, like.
So what is the definition of positive definite? It has to have symmetric, is it?
Yes.
So I should not say Cartan matrix as a symmetric one actually, positive definite one. Okay. So I should, yeah, but yeah, I mean, let's think actually. So symmetric matrices, the positive definite matrices need to have symmetric and these things. So yeah, so you just don't say it is symmetric actually, it's positive definite. But whatever this matrix, does one know this matrix, what you call as from linear algebra, these EIEJs, what it is called as?
That gram matrix.
Very good. This is just nothing but gram matrix. But this is indeed a positive definite. Do you have any objection to that? Can you tell me why it is a positive definite?
It's a symmetric bilinear form.
Of course, and it is a positive definite bilinear form, right? Isn't it?
Yes.
See, EIEJs are nothing but, I mean, like they are unit vectors, no? Isn't it?
Yes, yes, yes.
Okay. So this is, so yeah, so I should be careful. Cartan matrix, as it is not symmetric, so thanks to him, so he's to kind of correction that you cannot call it as a positive definite. Okay, fine. So yeah, now so this is well known, often it is called as a gram matrix. Okay, now so this is, we have with all these things that MII is equal to 1 and MIJs for I is not equal to J, it is belongs to this set 2, 3, 4, 6. Okay. Yeah. So far we are heading towards our goal. Now my question is, now here is the important thing when you do the mathematics. So question, suppose B of C dash is another basis of V with respect to chamber C dash, and G dash is its gram matrix as above. How G dash and G are related? So the answer is that G dash is same as G up to reordering of indices. Okay, this is very important statement. What does that mean? So this we will see in the assignment how do one kind of sees these things. So without loss of generality, we can concentrate on B of C, because any other matrix will be the reordering of indices. What does that what does that mean? What is this statement says? What mean by a reordering of indices?
Change basis ordering.
No, you see. So you have some permutation map on, suppose alpha 1, alpha 2, alpha L. Okay, that is just nothing but alpha sigma 1, alpha sigma 2. So reordering is mean that this G dash is nothing but this A sigma I, A sigma J actually. So what you have is G dash is, suppose your G is, let us say, Qij. G dash is nothing but A sigma I, sigma J. That is what you called up to permutation. These are the reorder. You just reorder your things, and that's what your ijth entry. So where sigma is indeed a permutation on this set 1 to L. Okay, so yeah, so a lot of properties are preserved with respect to these things. And how do you see that this is the case? This case follows from the fact that W acts simply transitively on the while chambers, which we will see. Okay, so far, yeah. Now, here is what we want to classify. Okay. Here is our question. So for L greater than equal to 1, let Mij belongs to N such that Mii is equal to 1 and Mij is greater than equal to 2. Then for I is not equal to j and Mij is equal to Mji, for what values of Mij, the gram matrix G positive definite. Okay. Yeah. So this will very much lead to the case of our how many root systems are there with respect to this graph. Note that this is very general problem, as we are assuming Mij's are greater than equal to 2. Okay. So be careful that we are achieving more than what we wanted actually should be. So this is what it is, the problem. And how do you get over these things? How do you solve? How do you get rid of this problem? And so here comes importance of graph theory. So we have Coxeter graph. What is the Coxeter graph? This is a usual graph. is a graph with which the indices with as the alpha i's, and we put edge between them if and only if Mij is greater than 3. Okay, and if Mij is greater than 4, then we'll write Mij on the edge. Okay, so in case like suppose you have alpha I and alpha j, and suppose if Mij is equal to 3, then we will simply have one edge. We will not write anything if Mij is 3. Or if Mij is greater than 4, you would always write this as Mij. This is how your terminology now. Okay, yeah. Now, as you know that, so what happens is, as our root system phi is irreducible, the Coxeter graph the corresponding is correct, the corresponding suppose as phi is irreducible, the corresponding Coxeter graphs remains connected. Okay, yeah, obviously. Why it is so? Can anybody guess why it is so? So if it is a disconnected, we will obviously get the two subsets of the base which are orthogonal to each other, which will contradict the definition of the irreducibility. Okay, so it's very obvious thing. I hope everybody is fine with it. So I will just pose for question if there are any. Okay. As G is positive definite matrix, we will call the corresponding Coxeter graph of G, say X, positive definite connected Coxeter graph. Okay, yeah, so that is what we have. So we call that as a positive definite graph. The main object is today is this object classify all connected positive definite Coxeter graph. So this is our main object today, which will eventually settle and the whatever the graphs related to the these things called as the Dinkin diagram. We'll come to that. Okay, so here is the thing. So what you have is first that we have for example, suppose these things. What is the for L equal to 2? What we expect the graph? This is anybody? So this is just nothing but 1 minus cos pi by p Is this matrix positive definite? Yeah?
Yes.
Where P is, yeah? It is? Anybody?
The positive definitely it is positive.
Yeah. So when does what is the equivalent condition for a symmetric matrix to be the positive definite? What is the necessary and sufficient condition? Somebody from the participant? Yeah?
Maximum value occur at the diagonal modulus?
No, in terms of the determinants.
All principal determinants are positive.
Positive.
Huh? Sorry? All?
Determinant of all principal submatrices.
Yeah. And so in this case, what is the determinant? 1 minus cos square pi by p, where p greater than
Pi by
2.
p.
Yeah, and so it is always less than 1 actually, this number. Yeah?
Yes.
Okay. I hope all of you are, and just it is a simple linear algebra, just these things. And so we have following, now we are having a task of classifying the Coxeter graphs, connected positive definite Coxeter graph. And so we'll begin with the observations or lemmas. Okay, the first thing is x is these things. X does not contain any cycle. Okay, so what will, if it contains some cycle, like yeah. So let us, these are m vectors, m is less than equal to L, and without lot of these things, just like E1, E2, these things, EM, right? What can you say? So consider these are, consider a vector V is equal to E1 plus dot 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 EM. Somebody from audience, determine its inner product. What will be it? What can you tell about this inner product? How many edges every vertices have? Yeah, E1 has how many edges are there?
Two edges.
Two edges actually. This thing, right? Yeah.
Yes.
So there are, so this is just nothing but, if you take what it is M plus EI EJ, where I is connected to J. Okay, I'm not writing 2 because I and J are arbitrary here. Okay, these things. Yeah. What about these things inside sum? Can one guess what will be? Yeah. Remember, what is EI EJ? What is EI EJ? No, EI EJ is always negative. What is that? Cos of pi MIJs. Okay. Here you will see that you will have a 2 into so you count that next thing that I is so you should not take repetitions here now. So not repetition is not allowed. So you just you just take such
You can
that
take the indexing to be I less than equal to J.
Sorry?
You can take the indexing to be I less than equal to J, then there
I
will be
less
no
than J.
repetition.
So that will kind of avoid these things. But what is the minimum value of, what is the minimum value of theta I theta j, EI EJ? It just, if it is a non-zero, what will be it? It will be a minus half, right? And how many indices are there as it is a cycle? See, it is very easy thing. You determine from here actually. Okay. I hope the participants are more active in the calculations. Actually, it is a merely a calculation. It is not a theoretical aspect actually. Here, it all boils down to the calculations. And so just be with me in the calculation. Okay. So to make things more interesting. So this would be like you will have M. This is less than equal to the maximum value is minus 1/2 or these things. So into 2 into, I don't know, minus M by 2. These are M members and this is equal to 0, less than equal to 0. And so this cannot happen. So I leave it this to maybe in assignment we can again move to these things because this is a mere calculation. And so V of V is less than equal to 0, which contradicts the positive definiteness of the bilinear form. Okay. Next is very important. What we have is second lemma is consider a positive definite connected graph X. Let I be any vertex of X. And let Ni G such that G is connected to I. Then summation Qij square is strictly less than 1. You note that G is nothing but matrix Qij's. You write as these things. So these entries, the sum of the squares of the entries where J belongs to Ni is less than equal to 1, strictly less than 1. Okay. This is very important because it will, this lemma is what actually helps us in the proving that that kind of which annihilates lot of cases. Okay. So let us try to prove this thing. So suppose you have J and J. So suppose Ni. Suppose proof J and J dash belongs to Ni. Do J and J dash will have edge between them? Yeah. What will happen if J and J dash will have edge?
There is a
Suman?
loop, graph is connected.
Huh?
There will be cycle.
There will be a cycle. Very good. So if J and J dash has edge, J and J dash are connected by the edge, then there will be a cycle which will contradict the lemma of 1. Okay. Yeah. And so all so there is no edge between the indices in Ni. Okay, fine. So we are at here, and what you will do to prove this result? The next thing is to consider let E1, E2, ER belongs to Ni without loss of generality, just taking the order as for our convenience. Okay. And I mean, I can start with anything, right? Consider the vector space, consider the subspace. F, which is equal to summation REI, REJ, J belongs to J. Okay. So what is the inner product between EJ and J prime when J and J prime belongs to Ni? Please, some of audience. Yeah, Suman, what will be the inner product?
Cos of pi.
No, see, there is no edge. So what can you say? If there is a no edge, I mean, see, that, yeah, so I should have mentioned it earlier. So if there is a no edge, this your Mij is must be 2, right? Isn't it? So this is always 0. This is non-zero if and only if there is an edge. Do you agree with this thing? See, initially when we have these things, when I have defined the Coxeter thing, I have mentioned that we will mention that these things on these things Mij's and 3's and Mij's 4. So it means that when you will have no edge, you will have this Mij's are 2, and so I mean cos pi by 2 is 0, and so you will have this thing is equal to, sorry, this thing is equal to 0. So these are all orthonormal vectors. So Ej's, J belongs to J, J belongs to Ni. These are all okay. Now I would like to, so what is the distance? Consider the distance d between Ei and the subspace F, which is summation J from Ni Rej. Does one know how to determine the distance between these things, one vector and its subspace? A linear algebra question. What you will do?
Orthogonal projections.
Very nice, Namuturian. And so what is its orthogonal projection? What is orthogonal projection Ei on F? This space F? Yeah? See, this is a linear algebra, but I am happy at least somebody so. So this, it's orthogonal projection of Ei on F.
Yeah.
Orthogonal.
Ei minus the inner product of Ei with.
No. See, orthogonal projection will be the some element here of F actually. Okay. And the difference, the distance is these things. So I want its projection here. What will be this element? So suppose this is the basis, it's orthonormal basis. So that element, that alpha, orthogonal projection of Ei on F is given by the vector alpha, which is nothing but summation Ei Ej square. This is norm of Ej square Ej, but this is 1. So this is your element here. Its projection lies on these things. So this is an vector of element of F. And what is the distance? The d square is nothing but norm of Ei minus alpha square. What it is? Ei minus summation Ei Ej Ei minus summation Ei Ej. This is equal to what it is coming to be? Do the calculation. See, once the calculation starts, my tendency is to become very slow. So I urge you to do the calculation. So anyway, but you are not giving me any option now. So this is the thing, summation EIEJ square minus summation again EIEJ square, and this is nothing but summation EIEJ square. And so you will have but what is this? This is just nothing but, so EI is 1, this is nothing but QIJ square, and this is your D square. So has to be greater than 0, and that would imply that summation QIJ square is strictly less than 1. Okay, so this is a very important result, nullifies many cases actually. Okay, so yeah, so fine. Again, so we have several lemmas. The next one is so we have in two parts that X is positive definite connected graph, then any subgraph of X is positive definite. Okay, and another B, which is very important and called as a shrinking lemma. Okay, now what does this say is that if X and Y are any no so suppose X1 and X2 are any subgraphs of X such that and the point of X, the terminating point, I don't know this is a correct notion in graph theory, and terminating vertex of X and originating terminating vertex of Y1 and originating vertex of Y2 is connected by simply laced graph. This is a new terminology. What is that? A graph is said to be a simply laced if all its edges are simple edges, means there is mij's is 3. So it is simply laced if this is a simply laced, if all mij's are 3, which we don't denote. So that is the thing. So this is a simply laced graph. This is mij's are 3 with the edges. Okay. These are simply laced. Then the terminating point of y1 and originating of y2 can be shrink to a point. Okay, so suppose what is here? So your ambient these things, and suppose this is your y1, and so suppose this is your y2. So it is started. This is its ending point, and this is your point. And so these 2 points, these are connected by simply laced graph. This could be a 4, 6, or these things, but this is 3 all the time. And so what this result says that you can have these things, and this graph, you can shrink these 2 points become 1 point and remain these things, this point, and the resulting graph still is positive definite. It's a very important result. I urge you to see a Bourbaki or Humphreys to see its proof. Okay. I'm not going to entertain this, but just, I mean, it's not very difficult, and I urge you to see the book. Yes. So, right. So this was the last thing which we needed. And yeah. So, fine. I mean, these all lemmas will lead us to the classification. Okay. Now, what we have is an applications of lemmas. If there exists a vertex, okay, of degree 3. What mean by degree 3? Degree 3 of vertex. So it means that this has 3 hands. 1, 2, 3. There are at least 3 hands. Okay. Then, so suppose application, if in the X there exists a vertex, in the Coxeter graph X there is a vertex of degree less than 3, then you can't have, so you will have only a simply laced graph there actually. Okay. So just hold on. I just see what I am writing is correct or not. Yeah. So degree 3, then all its edges will be simply laced. Then all its edges like this type. You can't have a double edge. I mean, like, you can't have here a 4, 3, 4, 6. These kind of numbers you will not have. Your MIJs will be always 3. Okay. So this case is nullified. Why this case is nullified? Can one tell me? Suppose this is the case where which lemma it contradicts? Who is a specialist in graph theory here? and you don't need space list also. Yeah. I claim that it contradicts the lemma too. That is the hint. So suppose you have here E1, E2, E3, E4. Okay. What is this? This is Q23, Q12, and Q24. What is Q12 square, Q23 square, and Q24 square? Tell me this number. What will be this number? What will be this number, Snehashish?
Sir, isn't it 3 cos pi by 3 whole square?
Huh? No, I want with values.
Pi by 3, so 60 half. 3 by 2 cos.
No, see, it will be 1 by, see, for this Q12 is 1 by 2 square. Okay?
Yes.
And this is Q23. Q23 is root 2 by 2 square. Yeah?
Okay. Sorry.
And this is 1 by 4. Again 1 by 2 square actually, right? Q24, these things. Right? How I'm writing? Just by knowing the values actually of cos 60 and cos whatever, pi by 4 or something like that. So it's, I'm not doing rocket science. Okay? And so this is just nothing but 1 by 4 plus 1 by 4 plus 2 by 4. This is just nothing but 1 by 2, and this is equal to 1, which contradicts that the sum of all these things is less than 1. Okay? So these 2, 3, 4, they join this 2, and so this contradicts the lemma 1. Okay? Fine. Similarly, application 2. If there is an edge with Mij is equal to 6, then you should have L is equal to 2. Here, suppose I have these things, and here I have 6. I say that I am in trouble. Again, it will contradict the lemma 2. Now, this should actually solve by somebody. So, what is Sanu? How it will contradict?
I am not focusing
you are
more
not
details
focusing.
actually. It's that
Okay.
yeah, more time I have to spend on it. Sorry, sir.
Okay.
Actually, these
No
are
issue,
very
no issue.
confusing.
At least you are honest. Anyway, chalo. This will again. So suppose you have 1, 2, 3. Okay. So you will have Q12 square and Q23 square. So Q12 square, if you assume minimum 1, this will be 1 by 2 square. What will be Q23 square? If you have what is minus cos pi by 6 square, I mean, what is cos pi by 6?
Root 3
What is the
upon
value of cos pi by 6?
root 3 upon 2.
Root 3 by 2 square. Again, this will give us 1 by 4 plus 3 by 4, which is 1. So contradicting again lemma 2. Okay.
So, here edges 1 and 2 are connected. That's why we are taking Mij to be minimum 3.
Sorry?
We are taking A1 to square to be 1 by 2 here, na?
So, no, why we are taking here 3? Because
no,
4
sir.
is more.
Yes, sir. That's what I am saying. That
that's
these
what
two
it is,
edges.
a less than minimum value we are taking actually. Okay.
Yes, but x1 and 2 are connected. That's why we are taking Mij to be for minimum value.
Correct. We could simply have 4 or 6 actually, but that will give a even worse condition actually here. Okay. You understand?
Sir, how in previous, sir, we take Q2, 3?
Which one?
In
Which one? Sorry.
Previous previous application, first application. Here we taken Q2, 3 to be 1 upon 2. 1
No,
upon
no,
root
no.
2.
Q23 is root 2 by 2 square. Q23 square is root 2 by 2 square.
So what is the, sir, Mij value here?
Here
What
4.
is?
Q23 is 4 here. It is 4. It is written here. You see here.
Oh, okay,
4.
okay, sir. Okay,
Yeah?
okay, sir.
Is it
Understood.
clear,
Yes.
Aditya? Okay.
Yes, sir. Yes, sir. Clear.
Okay. Yeah. And so again, this is the lemma. Sorry, application. A vertex. A vertex cannot belong to two distinct edges of order like of with Mij's is equal to Mij is greater than 4. So suppose you have a vertex here and this Mij is 4. What we will have? Again the same thing, right? This will be root 2 by 2 square plus root 2 by 2 square. This will be what will be its value? Its value will be 1. The contradiction actually. Yeah. So these are the things. And once you have those things, now all these things, as you see that the applications of lemma, you and the shrinking lemma, everything. And so you will come up with these all the graphs here now, which I am writing. But I'm hiding you a lot of calculations because of the time, but I urge all of audience at least once in their this career they should do mathematical career, they should do this checking the book of all the classifications of all the graphs actually. So here are all we have is, so I just need a new page here. So this is the first graph. If you do systematically this thing, so these are L vertices. This is known as AL. Here the last one is this thing. Here this makes sense only when you have L greater than 2. The third one is DL. Fourth one is F4. Oh, this is G2. Then you will have F4. Then you will have H3. H4. This is called as I2P. This is actually a dihedral group. and the special one, the exceptional ones, E6. This is E7, and similarly you will have E8. Okay. Yeah, if one knows the Lie algebras, at least classical, you will see that one case is missing here. Which one is missing?
CL.
Yes. And why that is so, Amit?
I don't know.
Anybody from audience?
Because we are not specifying which is the long route or short route.
Very nice actually. So because we have, I mean, we have normalized the norm, no? I mean, we have taken these things. So what happens is that, so here is the thing. So the difference is as we have this configuration does not reveal us the length of simple roots. Okay, and so how to get back this thing? Yeah, and so what is that thing is that you have to make, see, the difference is in this thing. So what you will do is that we will put the arrows towards the which one is the long route. Or so suppose you have, so this is your Mij is 4. Okay, what do you see the length? Suppose alpha 1 is a bigger than alpha 2. Okay, then you will write as like this thing. It's a greater than symbol. What is the difference? What is alpha 1 norm alpha 2? Anybody knows from the graph? What is this? Just quickly go to the graph, you will get. What it is? I guess everybody is in the another zone now anyway, except Amit, I guess. So yeah, so it's, I think, root 2. And so similarly, if you have 6, then again it is the root 3. And then again you will make sure, suppose this one bigger is that, and you will see that you will need the corresponding changes, and you will write. And those diagram, if you do, those are called as a Dynkin diagram. So let me write down the Dynkin diagram and the new page. Nothing change happens to the first one. BL supposed to be have change because BL has always these all L minus 1 roots have the bigger length here and L greater than 2. And so you should consider the one root which is having bigger length than the all L minus roots, which is nothing but just a transpose of that matrix. Here you get L greater than 3 vertices. Otherwise, it will be same as maybe B2 again. So this is a CL. DL, you as are, they are simply list. Even if you do here, there is a no change. These are all L greater than 4 matrices. L equal to 3 is again, it will be A3. Okay. And then you will have E6, E7, E8, okay, and these F4, these are the special things. In F4, either you can have this way or this way, but they are both, they will be just nothing but a change of matrix, change by permutation of those things, because the length of the other two sides are, I mean, it's just there will be no major change. And G2 again, and there will be no major change, either you put this side or that side. The convention, we put the first vector as a bigger thing. Okay. And why I am not writing others? Because these are the only matrices which Q's U correspond to the actual simple Lie algebras. Okay. Right. This one gives you these matrices, gives you the classification of simple Lie algebras. And you see these, as Professor Shraddha actually introduced, these correspond to the, these are the Lie algebras who correspond to these Lie groups, SLN Cs, SLN R, and all these things, SON, and so. And so these are the classical Lie algebras, because you will see that this defined for arbitrary L. But unlike these things, these are the exceptional ones. Although the Lie algebra exists with the corresponding root structure, actually corresponding root system, but these are the special ones. And whatever you have is the classical one here. Okay, which kind of these things. So these, as often it is said that what we are doing is in the Lie algebra thing is advanced linear algebras. In case of Lie groups, you always have to deal with the topology and the geometry of the structure actually. And so it is a, you sometimes kind of dealing with the topology is not that easy. And so a major thing in mathematics is that to simplify that thing. So we tangentify the difficulty itself actually. So what we mean by tangentifying difficulty, it means that considering its tangent space at origin, which is just nothing but the left invariant vector fields on your differential manifold, and those have that form of, they satisfy this Jacobi identity, and they have naturally, you can identify with them the Lie algebras. And actually studying Lie algebras reveal more or less almost every information of the Lie groups, and that's why the people study Lie algebras. But one should be honest to admit that the existence of the Lie algebras, of course, is from the Lie groups. Okay, so at least for finite dimensional. For infinite dimensional character algebra, I don't think this argument will hold any water. But for finite dimensional simple Lie algebras, of course, there is origin from the Lie groups, and we study because they help us a lot to give an information of the symmetries. Symmetries are nothing but the groups of those things. Okay, so saying this thing, I stop this lecture things, set of lectures, and I thank you to all for paying attention to it. Okay. So thank you.
Yeah.
Well, so thanks to Sachin for delivering these lectures. So we are actually breaking the trend here by delivering lectures despite being organizers. Yeah, in AIS normally that doesn't happen. So here are claps for Sachin.
Thank you. Thank you.
Okay, we can stop the recording and maybe take a couple of questions.